Hello, my name is Marty Marinack. I'm currently attending Carnegie Mellon University, where I work with Professor Fred Higgs in the Particle Flow and Tribology lab. And my research focus right now is on granular flows in tribology. I heard about STLE through my participation at the IJTC conference last fall, and since then I went on the website and started to learn a little bit about STLE, and one of the things I really liked was how active STLE is in getting students involved, so I decided to join earlier this year and get involved right away in the poster competition. I'm really just getting started, but already it's definitely making a difference. As a student looking to start a career very soon, being able to attend a meeting such as this one is very important for networking, meeting people, getting my research out there. And STLE has really helped in making that possible for myself and other students through things like the student poster competition, as well as opportunities like the Young Tribologist Conference Award, which I was actually fortunate enough to receive this year, and which is providing hotel rooms. What we're looking at here is, as you can see, it's titled an Eulerian Lattice-based Cellular Automata Approach for Modeling Multiphase Flow Tribology. And what we're looking at is, as many know, multiphase flows are very prevalent in a lot of tribological applications like artificial hip wear, chemical mechanical polishing. And so what we're looking to do is take existing methods, particularly an Eulerian Lagrangian method, where we're tracking the particle locations and speeds, and we're looking to get away a little bit from the traditional method, which is the discrete element method to model particles, and look for something first order and computationally fast. So we're looking to combine CFD with a method called cellular automata to give some increase in speed for these modeling processes. And so what we're able to find is that by combining these two methods, computational fluid dynamics and cellular automata, we did some validation studies to show that we can produce some viable results. And the real important finding in our studies was that we can get a huge time savings by using our new method. So when we look at just one quick example, when we model 10,000 particles in a simple flow situation like Couette flow, using the Eulerian DEM method, it takes about 12 hours. If we use the new method that we're working on developing, we can do this in about 5 minutes. And so one of the things is that there's obviously an accuracy trade-off, and so we definitely don't propose this as any sort of replacement to existing methods, but maybe more as a supplement to those methods, or something we could run before running those methods to get some quick results. Right now it's still very general since we're sort of developing a technique, but I would say somewhere where it could be most useful is any sort of system where you have a large amount of variables that are going to affect the outcome. So one example we have here is sort of like an erosive wear study, maybe with sand particles on a propeller blade, or any sort of study like that where you have a lot of variables affecting the solution. And what you might want to do is, before you run a lot of high fidelity studies that are going to take up a lot of time and eat up a lot of computation time, you maybe use this method to decide which variables most strongly affect the system, and then researchers and developers can just pick those variables for more high fidelity studies and save, obviously we're talking about 12 hours, 10,000 particles. As that ramps up, save weeks or months of time in developing different products and techniques. I'm not sure it would cost very much because this is really just a computer-based method, but actually I think it really could end up saving a lot of money when you're talking about computation time and processors. For instance, we just run these studies on a basic desktop computer, and we're able to do 10,000 or 300,000 particles in a matter of minutes or hours. So it could probably save, I would imagine it could save companies and researchers a lot of money in terms of the need to buy powerful computer clusters or things like that. Instead, you could buy simpler systems, less expensive systems, and be able to run these simulations.